In this Intro to Data Science section, we're going to talk about dynamic visualization, and we'll do that over the course of a couple of videos here. Now, you may recall from the preceding Intro to Data Science section where we first introduced static visualizations that we did a die rolling simulation. We rolled a six-sided die some number of times, and we talked about the fact that if it's truly random, each of those six values has an equal probability or likelihood of being chosen every time we pick a random number. So every die face on a six-sided die has approximately a 1/6 chance of being chosen on a given random roll, and that equates to approximately 16.667%. Now, you may recall that we ran that static visualization several times. First, we started with only 600 die rolls, and we saw that yes, all of the die faces came out close to 100 each, which is what we would expect if we have 600 total die rolls, but they weren't so close that the bars looked to be about the same height. Then we ran the example again and we did 60,000 rolls, and now the bar heights were getting closer to being even, and then we took it a step further and did 6 million rolls, and we got nearly 1 million of each of the different faces. And those static visualizations were helpful for starting to understand the law of large numbers, which shows that as we roll those dice more and more and more, that we narrow in on or close in on the 16.667% we expect for each of those die faces. Now, as helpful as that was, to really get a sense of the law of large numbers in action, it's helpful to do it with an animated visualization, a dynamic visualization that changes as we roll the dice. And that's what we're going to focus on in this example. So in our static visualizations, we ran the simulation first, then displayed the results. With dynamic visualizations, we're going to take advantage of a capability from the Matplotlib visualization library called a func animation, in which we use a function to drive an animation that updates the visualization dynamically every period of time in our particular case. So as you'll see momentarily, every approximately 33 milliseconds, we're going to update what is presented on the screen, so the bars will be jumping and dancing, and you'll really get a sense of the law of large numbers in action. Now, the way func animation works is it drives an animation one frame at a time, what we call a frame by frame animation. Every animation frame is going to specify everything about the diagram that needs to be updated during one individual update. And by stringing a whole bunch of these things together, we will get that animated effect that we're looking for. Now, in this example, every animation frame we create is going to roll the dice a specified number of times, and as you'll see momentarily, we've created this as a script where you can specify arguments to the script that indicate how many dice to roll and how many animation frames to perform. We're going to, on each frame, clear the current visualization that we had already displayed and create an entirely new visualization with all of the updated die frequency information. Now, the more frames per second you can display, the smoother your animation is going to appear. So for example, video games with fast-moving elements in them generally are going to try to aim for at least 30 frames per second, and nowadays it's not uncommon to have 60 frames per second or higher for some of these gaming devices that are now available to us. The amount of work, however, that you do in each of the animation frames in a func animation can affect your animation speed. So we do want to try to minimize the amount of work we do in each frame to keep that smooth animation going. And in this example I mentioned a moment ago, we're going to use approximately 33 milliseconds between our animation frames, which will give us about 30 frames per second. So if you divide 1,000 milliseconds by 33 milliseconds, that gives you about 30 frames per second being displayed. So let's actually demonstrate the final result, and then in the next video we'll start talking about the code that enabled us to build the dynamic visualization. So let me switch over to a terminal window here. You can see I've listed out the contents of my CH06 folder, which contains all of the code for the lesson we're currently talking about, and the script that we're going to look at starting in the next video is defined in the roll die dynamic .py file. So if I would like to run this file, I'm going to go ahead and type IPython followed by the name of the file, and this particular example also demonstrates for the first time how to process command line arguments in Python, and we're going to allow this script to receive two command line arguments. The first one is going to represent the number of animation frames we would like to perform in total. So this is going to also control the overall duration of my animation. So let's say I wanted to do 6,000 animation frames, and the second command line argument is going to represent the number of dice to roll in each animation frame. And to start out, I'm going to do 6,000 animation frames, one die roll at a time. So that's going to enable us to really see the bars changing on a die by die or a roll by roll basis. So let me go ahead and run that and get that on the screen here, and we'll get a chance to see it in action. And then after I let this run for a little bit here, we'll kill it off and start it up again, rolling more dice at a time per frame. So as you can see here, it's pretty slow in terms of updating, but there's a couple of things that you can see going on here. First of all, the dynamic visualization, so you do see the bars and the text changing as we roll the dice, and you can see how many die rolls there are at a given time here. Also notice that Matplotlib and Seaborn, the two libraries that we're using for the visualization here, are capable of dynamically adjusting the y-axis here to represent the magnitudes of the bars that we have. So this, the longest bar is affecting the total height of the diagram at any given time. And so right now we have more fives than we have of anything else. Over 20% of our rolls so far have been fives. Now it's decreasing a little bit. But you can see the bar heights are bouncing around. The number of each face is changing dynamically. So I'm going to go ahead and kill this off here because it's kind of slow when we're only rolling one at a time. So we'd have to wait a pretty long time before those bars actually balance out to demonstrate that law of large numbers in action. So what we're going to do next is run this thing again, but this time let's say we want to do 10,000 animation frames. Actually, it doesn't really matter because I'm going to cut it off a little bit short, but let's say we want to roll 600 dice at a time. So if I roll 600 dice at a time, that's 600 dice, and we're trying to do that 30 times per second. So that's 18,000 dice per second that we want to roll to try to see how that affects the animation in this case. So let's go ahead and run that. And in a moment the window will pop up and you can see it's cranking through die rolls super quickly now. But notice right away that the bars are already starting to even out and that all of our percentages are in the 16% range. So you can now really see that law of large numbers in action. The more dice we roll, the faster we converge on 16.667%. So we're already up to 160,000 plus rolls here, and the bars are almost even in height based on the current die frequency values. So this really emphasizes that law of large numbers in action. So we're going to terminate this by closing the window, and in the next video I'm going to show you how we created that animation in the context of the roll die dynamic.py script.